Close your eyes for a moment. Imagine the sky above, not just as a dark canvas sprinkled with stars, but as a living record of billions of families scattered across the universe. Each star is not alone. Around many of them, worlds gather, circling in silence, warmed by light, or drifting in shadow. These are solar systems, cradles of planets, moons, dust, and mysteries. The word sounds simple, almost ordinary, yet hidden inside it is everything we know about home and everything we dream about elsewhere. For in the story of solar systems, we discover not only how our Earth came to be, but also how countless other worlds might be waiting, far beyond reach. Tonight, as you drift towards sleep, let us wander through this tale, not in haste, but in a slow rhythm like the orbit of a planet. Each step will lead gently to the next, like ripples across water. The facts will not stand cold and sharp. They will arrive as soft lanterns in the dark, carrying both knowledge and wonder. Listen closely and let the science of solar systems become a lullaby of the cosmos. When stars gather their families, stars are rarely born alone. In the beginning, when a star emerges from its cloud of gas, it does so surrounded by leftovers, dust, ice, fragments too small to ignite. Gravity does not waste these scraps. It shapes them into companions. Some grow into planets, some remain wandering rocks, and some dissolve into rings of dust. A solar system is not merely built, it is gathered like a family slowly forming around a fire. And isn't it curious how one star can give rise to a dozen unique worlds, each different, yet bound to the same center? The fact is simple. More than half the stars in our galaxy have such families, perhaps even more. Yet each arrangement feels like a fingerprint, never repeated, always unique. Our own sun is but one of hundreds of billions in this grand cosmic nursery. The image of a star at the center with companions circling is comforting like a hearth, but it is also fragile. Systems can form, scatter, and reform. Some planets are thrown out entirely, left to wander the galaxy in darkness. Others are captured, adopted by passing stars. Solar systems, then, are not just mechanical structures. They are dynamic, changing, almost alive. What makes this truth even more remarkable is that it connects us to an unseen kinship. Somewhere out there, another star shines on its orbiting children, while we, here, look up and call it simply a star. But to any beings under its light, it is home. And this recognition that we are part of something repeating across the galaxy gives both humility and wonder. The birth of solar systems begins with stars, yes, but to understand their true character, we must step backward further into the cloud from which stars themselves are born. A quiet definition of a solar system. When we say solar system, we often imagine ours, sun at the center, 8 planets in neat order. But in truth, a solar system is any star and the bodies it holds in its gravity. The definition is quiet, precise, yet endlessly flexible. Some systems may host giant planets hugging their star so closely they orbit in days. Others may have icy belts stretching for billions of kilometers. Some may host moons larger than our own planet. This definition anchors us. It tells us wherever there is a star, there may be a system. Yet the beauty lies in variation. Our solar system, with rocky inner planets, gas giants farther out, and icy fragments at the edge, is just one example among countless. Astronomers have found systems with 3 suns, systems with no Earth-like planets at all, and systems where worlds orbit in perfect chains, locked together by invisible rhythms. The quiet power of the definition is that it contains both order and surprise. Gravity is the binding law, but within that law, nature improvises. A solar system, then, is both structure and story. It is predictable, yet filled with wonders no human imagination could have invented. Think of how different the perspective becomes when you look at the night sky. Each point of light is not only a star, but also a potential community of worlds. Tens of billions of such communities exist, spread like seeds across the galaxy. This is not speculation. It is one of the strongest conclusions of modern astronomy. Solar systems are the norm, not the exception. And so the journey of discovery cannot remain at definitions. It must carry us to origins, to where clouds of gas, vast beyond comprehension, give birth not only to stars, but to everything that surrounds them. The cloud before everything, giant molecular nurseries. Every solar system begins in darkness, hidden within a giant molecular cloud. These clouds stretch for light years, cold and silent, yet pregnant with possibility. They are made of hydrogen, helium, and traces of heavier elements, dust, ice, carbon-rich molecules. Within them, stars are born in clusters, sometimes hundreds at a time. Imagine a city of newborn suns, all glowing softly, each preparing to gather its own family. The cloud itself is restless. Turbulence stirs it, nearby supernovae compress it, and gravity begins to weave threads through its fabric. Denser knots form, collapsing slowly like beads sliding along a string. Within these knots, temperatures rise, and at their centers, stars ignite. Around each new star, the remaining material flattens into a disk, the raw canvas of a solar system. The astonishing truth is that these nurseries create not only stars, but also the chemical ingredients for life. Complex molecules, alcohols, amino acids, have been detected in such clouds. This means that before Earth existed, before our sun was even lit, the universe was already preparing the recipe of life within these dark, cold regions. We seldom think of clouds as places of creation. Yet in space, clouds are wombs. They are the beginnings of everything solid, liquid, and living. Our own solar system traces back to such a cloud 4.5 billion years ago. Within it, the story of Earth, oceans, mountains, and even ourselves began, though we were still dust. From these nurseries, the next stage unfolds, gravity tightening its hold, spinning material into shapes that will one day become planets. Gravity's first whisper. Collapse and spin. It begins quietly. A fragment of a cloud grows dense enough for gravity to dominate. Gas and dust spiral inward, not falling straight but turning, caught in a slow whirl. Conservation of momentum ensures the more it collapses, the faster it spins. A flattened disk forms like dough pressed under invisible hands. At the center, pressure mounts until fusion lights the newborn star. Around it, the leftovers remain, destined to become a solar system. This whisper of collapse is universal. Every star you see in the sky once spun within such a disk. And within these disks, the seeds of planets are sown. The rotation is not random. It defines the future orbits, the tilt of planets, the symmetry of moons. Even our own Earth's year, our day and night, owe themselves to this ancient spin. There's a subtle elegance in the process. The same law that sends skaters twirling faster as they draw in their arms also governs the birth of solar systems. It is a simple principle, yet it sculpts the architecture of worlds. It ensures that across the galaxy, stars and planets are not scattered haphazardly, but arranged in flattened harmony. The whisper of gravity becomes a roar over millions of years as fragments collide, merge, and carve out stable paths. Chaos slowly cools into order. In this way, the first whispers become the blueprint for a system's entire history. Even billions of years later, planets still follow the same orbit set during those early spins. And as the spinning disk takes form, a ladder of heat and cold emerges across its span, deciding which worlds will be rocky, which will be gaseous, and which will be cloaked in ice. A disk of dust and dreams, proto-planetary beginnings. Picture it. a wide, glowing disk around a young star, its center bright, its edges dim. The material is uneven, hot near the star, cool at the outer rim. Dust grains stick together, forming clumps, then pebbles, then larger bodies. These are protoplanetary disks, and within them every planet begins as dust. It is a quiet miracle, the transformation from tiny grains to entire worlds. At first, the collisions are gentle. Static charges, microscopic stickiness, allow particles to cling. Over time, gravity takes over, pulling fragments into larger and larger clumps. In these collisions lies the destiny of planets. Some will grow massive, others will remain small. Some will gather gas, others will stay rocky. The disk, though chaotic, is the womb of order. It may surprise you to know that astronomers have photographed such disks around young stars today. Rings, gaps, and spirals are visible, as though we are watching creation in real time. Each image is a snapshot of planetary systems in their infancy, a cosmic nursery captured across light years. When we look at them, we see not only alien worlds forming, but also a reflection of our own earliest history. And what a delicate history it is. A tiny change, a fragment thrown off course, a collision too violent, can alter the architecture of a system forever. Solar systems are both inevitable and fragile, both common and unique. They emerge by the same rules, but no two are the same. This balance of predictability and chance is what makes the study of them endlessly fascinating. From disks of dust and dreams, the next stages unfold. Heat, ice, and distance begin to separate fates, carving paths for worlds that will glow, worlds that will freeze, and worlds that will surprise us with possibilities still unknown. Heat, ice, and distance, the temperature ladder. In every protoplanetary disk, there is a hidden boundary where everything changes. Close to the star, it is too hot for ice to survive. Farther away, the cold allows frozen water, methane, and ammonia to exist. This invisible line, called the snow line, divides the destiny of planets. Inside it, rocky worlds are born. Beyond it, giants of gas and ice emerge. The arrangement is not random. It is temperature that decides who gets stone, who gets gas, and who gets ice. This ladder of heat and cold is why our solar system looks the way it does. Mercury, Venus, Earth, and Mars, all rocky, small, and dense, formed inside the warm inner region. Jupiter, Saturn, Uranus, and Neptune, massive, gaseous, or icy, took shape in the colder, outer reaches. Without this balance, Earth might never have existed as it is. Too close, it would have been a furnace. Too far, a frozen sphere. Instead, it became a delicate in-between. Yet this is not just our story. Other systems show the same pattern, though often with unexpected twists. Astronomers have found giant planets orbiting so close to their stars that their atmospheres boil. Others, smaller and rocky, exist in distant orbits, frozen, yet still present. The snow line is not fixed. It shifts as the star grows brighter, pulling worlds into fates different from our own. What makes this so fascinating is the way small differences ripple into enormous consequences. A planet forming just a little closer or farther from the snow line can change its size, composition, and even its chance to host life. The tiniest adjustments in temperature across millions of years shape entire histories. This is the poetry of physics, the quiet laws that decide everything without ever speaking. And once these seeds take form, another miracle begins. Dust grows into stones, stones into boulders, and boulders into the first real building blocks of planets. Tiny seeds of worlds, dust grains to pebbles. It almost sounds unbelievable. Every planet you know began as dust, microscopic grains floating in a disk of gas, colliding so gently that static charge let them stick. At first, it was like dust on a shelf gathering into clumps. But those clumps became pebbles, and pebbles became larger. This was the first quiet step from nothing into something. tiny seeds of worlds taking shape where only gas once swirled. The process is fragile, too violent a collision, and particles shatter, too weak and they drift apart. Yet over millions of years, enough grains stick together to form rocks big enough for gravity to notice. Gravity then becomes the glue, pulling in more and more matter. What begins as a speck can grow into an object kilometers across, a planetesimal, the first ancestor of planets. Astronomers studying young stars have detected pebbles gathering this way. Radio telescopes reveal faint patterns in disks, rings where pebbles accumulate, gaps where planets may already be growing. It is like watching evolution in slow motion, not of life, but of landscapes. Each image we capture is not just science, it is a glimpse into the universal childhood of worlds. It is humbling to realize that Earth itself, with its oceans, mountains, and forests, began as dust. That everything we call home is made from the same microscopic grains once drifting in silence. The dust in your hand, the dust under your bed, it all carries the same history, a reminder that great things always begin impossibly small. And as these pebbles grew larger, they entered a new stage. Collisions became stronger, shaping not just stones, but worlds in the making, planetesimals large enough to compete for space and resources. From pebbles to planetesimals, gentle collisions, lasting shapes. Imagine thousands of rocky bodies, each a few kilometers across, orbiting the young star. These are planetesimals, the first solid chunks of a solar system. They collide, merge, and sometimes shatter, but overall they grow. Gravity now plays a bigger role. Once a planetesimal is massive enough, its pull attracts more material, accelerating its growth. The process is self-feeding, like a snowball rolling downhill. Not all survive. Some are broken apart, scattered into belts of rubble. Others merge to form planetary embryos, seeds large enough to shape the paths of smaller bodies around them. This stage is violent yet strangely constructive. Each collision is both destruction and creation, wiping away fragments yet building new bodies in the process. Solar systems are sculpted by impact, trial, and error. Our own asteroid belt is a frozen memory of this era. These are planetesimals that never grew into a full planet, perhaps because Jupiter's gravity disturbed their growth. They remain as fossils, telling us of a time when everything in the solar system was young and restless. To hold a meteorite in your hand is to touch a fragment of that ancient stage, a time before Earth even existed. The transition from dust to planetesimal is more than just growth, it is destiny. Once bodies reach this size, they have a future. They may become planets, moons, or simply rubble, but they will no longer vanish back into dust. They have crossed a threshold into permanence. The story of worlds begins here, in the quiet yet relentless work of collisions. And among these young bodies, a new competition begins. The embryos of planets fight for dominance, colliding and absorbing one another until only a handful remain. Embryo worlds compete, the era of protoplanets. At this stage, the solar system is crowded. Dozens of planetary embryos, each hundreds or thousands of kilometers wide, move in overlapping orbits. Their collisions are no longer gentle. They are cataclysmic, shaping the destinies of future planets. The Earth itself was born from such an era, formed by the merging of many embryos. Even the Moon may have been the result of one such titanic collision. These protoplanets are restless. Their orbits are unstable, constantly tugging on each other, swapping paths, and sometimes being ejected entirely. Some fall into the star, others are thrown outward, never to return. It is survival of the largest, but also survival of the luckiest. Chance plays as much a role as size. In this chaos, variety emerges. Some protoplanets develop atmospheres by holding on to gas. Others remain bare, rocky bodies. Their fates depend on timing, how quickly they grow, how near they are to the star, and how much material remains to feed them. The diversity of planets we see today reflects this ancient lottery of collisions and captures. Our own Earth stabilized after this turbulent era, but scars remain, the tilted axis of Uranus, the retrograde spin of Venus, even the craters on the Moon, all evidence of protoplanets colliding in the past. Solar systems are not born tidy, they are forged in fire and shaped by chaos. And through this competition, one invisible rule guided everything: the snow line. It was the dividing line that determined who would be small and rocky, and who would become a giant of gas and ice. The snow line's hidden influence. The snow line is not a wall but a threshold. Inside it, the heat of the young star evaporates water and other volatile compounds, leaving only rock and metal to form planets. Beyond it, ices survive, adding mass to growing bodies. This is why giant planets like Jupiter and Saturn could form. They had access to both rock and ice, allowing them to grow large enough to capture gas. Without the snow line, our solar system would not look the way it does. Earth lies just inside this line, where only rock could accumulate. Yet the presence of water here is explained by icy bodies that migrated inward, comets and asteroids, delivering the oceans we know today. In this sense, the snow line not only divides, but connects, sending gifts from the outer system inward, enriching rocky planets with water and carbon compounds. Life's story may owe itself to this fragile balance. In other systems, the snow line shifts depending on the brightness of the star. Around hotter stars, it lies farther out. Around cooler stars, it creeps inward, sometimes so close that icy planets form near the star itself. This shifting boundary creates astonishing diversity in the planets we observe elsewhere. The snow line is invisible to the eye, yet it decides the fate of worlds. It whispers where giants will rise, where oceans may flow, and where barren rocks will remain. It is one of the quiet architects of the universe, drawing a map for planets long before they even exist. And from this hidden influence, the inner solar systems emerge, those compact families of rocky planets that remind us of Mercury, Venus, Earth, and Mars. The architecture of the cosmos unfolds step by step, like a melody growing richer as it continues. Building the inner rocky crowd. Close to the star, only rock and metal can survive the heat. Out of these ingredients, small rocky planets begin to take shape. They are dense, compact, and often stripped of thick atmospheres by the star's early winds. This is why Mercury is little more than a scorched iron heart, why Venus is cloaked in a heavy blanket, and why Earth and Mars found a middle ground. The inner solar crowd is forged under pressure, close to the fire. Their small size may seem fragile, but it gives them something precious, solid surfaces. Unlike the giants further out, rocky planets allow mountains, rivers, volcanoes, and eventually, on one of them, life. This is a rare privilege in the universe. Most planets discovered so far are giants with no surface to stand on. Rocky planets are like gems, small but infinitely valuable. The story of the inner worlds is also the story of contrasts. One burns too hot, one suffocates in carbon, one trembles with scars, and one blossoms with life. Yet all share the same origin, carved by heat and proximity. Each is an experiment in how matter can arrange itself under the same rules, but with different outcomes. It's fascinating to think that in those early days, Earth could have easily ended up like Venus or Mars. A few changes in orbit, size, or atmosphere, and the story of life may never have begun. That fragility makes our place not ordinary, but extraordinary. And beyond this hot inner zone, new giants were forming, gathering material on a scale the rocky planets could never match. brewing, the outer giants. Farther from the star, the cold allows ices to remain solid. This changes everything. With rock, ice, and gas available, planets here can grow enormous. First come the rocky and icy cores, each many times the mass of Earth. Once large enough, they pull in hydrogen and helium from the disk, swelling into giants. Jupiter and Saturn are the result, vast, layered, and wrapped in thick atmospheres. Without the snow line, such giants would never exist. The giants are more than just big planets. They act as guardians and architects. Their immense gravity shapes the paths of comets and asteroids, sometimes shielding inner worlds from destruction, sometimes redirecting chaos toward them. Jupiter alone has been called the solar system's vacuum cleaner, sweeping up threats with its gravity well. Yet it also stirred the asteroid belt into chaos, preventing a planet from forming there. Saturn, with its delicate rings, is another story of balance. Its beauty hides a role as a stabilizer, its orbit influencing the rhythm of smaller bodies. Uranus and Neptune, colder and more distant, hold secrets in their icy cores, their tilted spins, and their stormy atmospheres. Each giant has its own story, its own influence on the solar system's balance. The fact that giants exist in almost every planetary system discovered so far shows their importance. Sometimes they migrate inward, becoming hot Jupiters, circling stars in just days. Sometimes they remain far out, shaping entire belts of comets. Their presence decides whether smaller planets inside may one day host life, or whether they will be lost in storms of debris. The giants brood slowly, but once they took form, the young star itself began to breathe and push back, changing the shape of everything around it. The breath of a young star, winds and radiation. A newborn star is restless. It shines brighter than expected, throws off bursts of radiation, and exhales powerful winds of charged particles. These stellar winds sweep across the disk, stripping away lighter gases near the star and sculpting the edges of the forming system. Close worlds are left bare while farther planets retain thick blankets of hydrogen and helium. The star decides with its breath which worlds will be thin and which will be bloated. Our Sun once went through this phase. Its winds likely blew away the thick early atmosphere of Mars, leaving it cold and fragile. Earth, larger and shielded by its magnetic field, survived with a delicate balance. Venus, meanwhile, kept its atmosphere but turned it into a suffocating greenhouse. The breath of the Sun left three siblings so near, yet so different. Such is the quiet power of stellar winds. Astronomers can see this happening elsewhere. Young stars often show glowing jets, streams of gas, ejected light years into space. These flows carry away excess energy and mark the transition from chaotic collapse to a stable star. Around them, disks of gas and dust thin out, clearing the stage for planets to take permanent paths. It is humbling to imagine that our home was once swept by these invisible storms. The air we breathe today is not the original. It is what survived, what endured the solar wind. This reminder connects us to a time when survival itself depended not on biology, but on the star's moods. And when those winds had carved enough space, the planets began to find order. Paths cleared, collisions lessened, and stable orbits emerged, like dancers finding rhythm in a once crowded floor. Disks, thinning, paths clearing. As millions of years passed, the protoplanetary disk began to thin. Gas was blown away by the star, dust settled into planets or was ejected into space. What remained was no longer a chaotic swarm, but a set of stable worlds tracing regular orbits. This clearing was the final act of formation. The solar system, once stormy and crowded, was now ordered, ready to endure for billions of years. Yet even in this new stability, small fragments remained. Asteroids, comets, and dust clouds lingered as reminders of what was left unfinished. These leftovers became more than debris. They became archives. In them, scientists today can study the early conditions of the solar system, reading them like fossils of space. The beauty of this thinning stage is that it is self-organizing. Gravity and radiation work together, sweeping the stage until only the largest and most resilient bodies remain. It is nature's quiet filter, leaving behind a structure we now call a solar system. Each orbit, each tilt, each distance is the result of this invisible sorting process. We know this not only from theory, but from observation. Around young stars, astronomers see disks with wide gaps, signs that planets have already cleared their lanes. In some, only faint rings of dust remain, circling like halos. These are systems caught in the act of becoming orderly. Watching them is like watching time-lapse footage of our own ancient past. And once paths are cleared, planets begin to fall into rhythms. Their orbits align, their interactions settle, and strange harmonies emerge in the form of resonances. Orbital highways and traffic rules. Planets do not simply wander wherever they please. They follow invisible highways of gravity, paths set by the star and shaped by each other. Over time, these highways become stable routes, like lanes on a cosmic road. Collisions lessen, predictability grows. A solar system becomes less a battlefield and more a dance floor. Each planet keeps to its path, held by the quiet but absolute law of gravity. Resonances often appear, patterns where orbits align in simple ratios. For example, one planet may orbit twice for every 3 of another. These rhythms act as traffic rules, preventing close encounters and maintaining harmony. Jupiter's moons are a famous example. Locked in such resonances, their orbits stabilized by rhythm. Similar patterns exist across planetary systems everywhere. The astonishing truth is that even chaos finds order. What once seemed random settles into predictable beats, like music finding tempo. This is why solar systems can survive for billions of years. Without these rules, orbits would decay, collisions would resume, and planets would scatter. Instead, they endure, quietly circling their star across ages longer than life itself. Yet these rules are not rigid. Sometimes a small shift can send ripples across the whole system. A migrating planet, a passing star, even a large comet can disrupt the balance, forcing planets into new highways. Systems are stable, but never frozen. They are alive with slow change, subtle adjustments over eons. And in this order lies a strange beauty. Solar systems are both fragile and eternal. They hold together because of laws older than time, yet remain sensitive to chance encounters. This balance is what gives them character, what makes each system unique in its architecture and rhythm. Resonances, rhythms that lock and guide. Imagine 2 planets circling a star, their orbits in tune like notes of a song. One completes 2 loops for every 3 of the other. This is resonance, an invisible rhythm that stabilizes their paths. It prevents collisions, keeps orbits steady, and creates harmony in chaos. We see this with Jupiter's moons, Io, Europa, and Ganymede, locked in a perfect chain of 1, 2, 4. Resonances are nature's way of weaving order into the cosmic dance. What makes them fascinating is their persistence. Once locked, they can last for billions of years, guiding moons, asteroids, and planets into predictable motions. Without them, many systems would collapse into chaos. They are subtle rules, yet they decide who stays safe and who drifts into danger. Think of them as the quiet traffic signals of the universe, unseen but obeyed. In our own solar system, Neptune and Pluto share such a resonance. Though their paths cross in projection, resonance ensures they never collide. Pluto always arrives at the crossing point when Neptune is far away. This delicate arrangement has lasted for eons, a reminder that precision and timing often matter more than raw power in survival. Resonances can also sculpt beauty. Saturn's rings, with their sharp gaps, owe much of their structure to resonances with the planet's moons. The gaps are not empty by chance, they are carved by rhythm, by moons tugging at particles until patterns emerge. What we see as elegance is really mathematics etched into ice and dust, chaos that stays peaceful. At first, the word chaos suggests destruction, but in solar systems, chaos often means unpredictability without collapse. Planets tug on one another, shifting orbits slightly, sometimes even wobbling in unexpected ways. Over millions of years, these small changes accumulate, creating patterns that look random, yet remain bounded. The system endures even as its details shift. This is peaceful chaos, the kind that stirs without breaking. Our own solar system has such behavior. The orbit of Mars, for example, is chaotic over long timescales. Its tilt and eccentricity shift in ways that cannot be predicted beyond tens of millions of years. Yet Earth and the other planets keep the system stable overall. This balance between unpredictability and endurance is part of the beauty of cosmic mechanics. Astronomers call it deterministic chaos. It means the rules are strict, but tiny changes in starting conditions lead to different outcomes. A dust grain shifted today may alter a planet's tilt billions of years later. It's humbling to think that such delicate sensitivity exists in something as massive as a solar system. This peaceful chaos also helps spread diversity. Asteroids scatter into new regions, comets are nudged into the inner system, and even planetary climates are influenced by slow, chaotic cycles. Life on Earth may owe its seasons and ice ages in part to this strange balance of stability and unpredictability. And while our solar system keeps its calm chaos, other systems show us more dramatic surprises. Giant planets moving inward, creating configurations once thought impossible. Hot Jupiters and their surprising journeys. When astronomers first began finding planets around other stars, they expected systems like ours. Instead, they found giants, Jupiter-sized worlds, hugging their stars so closely they complete an orbit in days. These hot Jupiters were a shock, rewriting what we thought was possible. Too close for comfort, too hot for atmospheres to survive quietly, they glow with heat, whipped by winds faster than sound. Their very existence raised a question: how did they get there? The answer lies in migration. These giants likely formed farther out where ice was abundant. Over time, interactions with the disk of gas and dust pulled them inward, spiraling closer and closer until they parked near the star. Some may even continue migrating, doomed to be swallowed by the star itself. Their journeys reveal that planetary systems are not static. They shift, evolve, and sometimes defy our neat categories. Hot Jupiters also reshape their homes. As they migrate inward, they disturb smaller planets, sometimes ejecting them, sometimes capturing them in resonances. They are bullies and architects, both destructive and creative. Systems with hot Jupiters may look sparse inside, with little room for Earth-like planets. Yet even here, diversity emerges. Some stars host both hot Jupiters and smaller companions, orbiting together in delicate balance. What's remarkable is that these discoveries came from unexpected signals, tiny dips in starlight as planets transited. Each dip revealed a giant skimming the face of its star, closer than Mercury is to our Sun, and each discovery reminded us the universe is stranger than prediction. It invents possibilities we never imagined. From these giants blazing close to their stars, we then notice another kind of planet, smaller but mysterious, filling the space between categories we once thought rigid. Migration. Planets that don't stay put. Planets are not fixed ornaments, they wander. Early in a system's history, interactions with the disk, with other planets, or even with passing stars can shift their orbits dramatically. Migration explains not only hot Jupiters, but also many super-Earths and mini-Neptunes we've found elsewhere. They may have started in one zone only to drift into another, changing their nature along the way. It is a reminder that orbits are not destiny. They are stories in motion. In our own solar system, migration likely shaped everything. Jupiter may have moved inward first, then outward again, dragging asteroids and scattering material across the system. This grand tack hypothesis suggests Earth itself owes its size and water to the dance of migrating giants. Without migration, our planet might have been smaller, drier, and far less hospitable. Migration can be smooth or violent. Sometimes planets spiral gently inward, carried by gas. Other times, gravitational encounters send them on sudden jumps. A planet may even be ejected completely, becoming a rogue, drifting alone through the galaxy. Migration is both creative and destructive, reshuffling the deck of worlds again and again. What fascinates scientists is the timing. A planet migrating too early may stop before it destabilizes others. Too late, and it may scatter entire systems. The balance of when and how migration occurs determines the architecture of the planets we observe today. Each system is like a frozen memory of its own migrations, locked into place when the disk finally vanished. And as we studied these migrating giants, we noticed another class, smaller than Neptune, larger than Earth, planets we never knew existed until other stars revealed them. Super-Earths and mini-Neptunes, the in-between worlds. Between the size of Earth and Neptune lies a mysterious category, super-Earths and mini-Neptunes. Our solar system has none, but they are the most common planets found around other stars. Some are rocky, a few times the size of Earth. Others are wrapped in thick atmospheres, small cousins of Neptune. They blur the lines between familiar categories, showing us that nature does not follow our neat definitions. Super-Earths are especially intriguing. If rocky, they might have stronger gravity, thicker atmospheres, and perhaps vast oceans. Some may be habitable, offering conditions where life could thrive. Mini-Neptunes, on the other hand, may have deep gas layers hiding exotic cores, perhaps even oceans under hydrogen skies. They challenge our imagination, reminding us that Earth-like does not mean Earth only. The fact that our solar system lacks these planets is itself a mystery. Did migration sweep them away? Did Jupiter's early motion prevent them from forming? Or are we simply unusual, one example of cosmic variety? Their absence makes us different, but also pushes us to wonder whether life thrives more easily in systems where they exist. What captures the imagination is the sheer number of these worlds. Every survey of exoplanets shows them dominating the galaxy, countless in their diversity. For every system like ours, there are many with in-between worlds circling their stars. To fall asleep thinking of them is to realize that the universe is richer than we ever expected. And from these in-between worlds, our journey drifts outward again toward stranger possibilities, where entire planets may be covered in oceans or glow with molten surfaces under eternal starlight. Water worlds and ocean depths without shores. Picture a planet covered entirely in water, no continents, no dry land, just endless oceans stretching for thousands of kilometers. These water worlds may exist in abundance across the galaxy. Some are super-Earths with deep oceans beneath thick atmospheres. Others may have oceans hidden under ice, warmed by internal heat. Their surfaces reflect starlight like mirrors, their waves stirred by alien winds. If life thrives anywhere, such planets may be strong candidates, for where water flows, possibility follows. The scale of these oceans defies imagination. On Earth, the Mariana Trench is nearly 11 kilometers deep, but on a water world, oceans could plunge hundreds of kilometers. with pressures so immense that exotic forms of ice, denser than rock, form at the bottom. Above them, liquid layers swirl, perhaps supporting strange marine ecosystems, unlike anything we know. The surface may seem calm, but beneath could lie an entire biosphere forever hidden from the skies. These worlds challenge our idea of habitability. Land, we assume, is necessary for life to evolve complexity. Yet water worlds might prove otherwise. Perhaps floating mats of organisms thrive in eternal oceans. Perhaps currents act as highways for life to spread. Or perhaps these planets remain silent, their waters sterile but beautiful. The unknown is part of their allure. Astronomers suspect water worlds exist because of how common water is in protoplanetary disks. Beyond the snowline, ice is abundant. If such planets form and migrate inward, they may carry their oceans with them. The very building blocks of life may be scattered widely, waiting for the right mix of conditions to awaken them. If Earth is a rare balance of land and sea, then water worlds may show us another path nature takes. And while oceans stretch outward in one direction, some worlds lean the other way, becoming seas of fire glowing with heat, their surfaces melted into rivers of lava planets glowing in starlight. Imagine standing on a world so close to its star that its surface never cools. Oceans here are not of water, but molten rock. These lava planets exist, discovered by their shimmering glow as they pass in front of their suns. Temperatures soar above 2,000 degrees Celsius, enough to melt iron. Their surfaces are seas of magma, with waves of fire instead of water. They are reminders that beauty often comes wrapped in extremes. One such planet, 55 Cancri E, orbits its star in less than 18 hours. Its surface is thought to be a landscape of molten rivers, cooled slightly on the night side but never fully solid. Each orbit subjects it to immense heat, keeping its crust in constant flux. To watch such a world would be like watching a furnace from space, beautiful, dangerous, unearthly. Lava planets remind us of Earth's youth. Our planet, too, was once a glowing sphere of molten rock, gradually cooling into crust and oceans. In a way, these planets are time machines, showing us what our home once looked like. But unlike Earth, many remain trapped in that fiery stage forever, held too close to their stars to escape the heat. They also teach us about composition. The materials vaporized from their surfaces can sometimes be detected in their atmospheres: sodium, calcium, silicates. By studying their spectra, scientists can glimpse the raw chemistry of worlds, stripped bare by fire. In their heat, they reveal secrets we cannot see elsewhere. From these fiery extremes, the journey drifts outward again, to planets of cold and distance, where ice giants hide their secrets behind blue-green veils. Ice giants with hidden warmth. Uranus and Neptune are often called ice giants, but the name can mislead. They are not frozen spheres. Instead, they are worlds of water, methane, and ammonia under immense pressure, layered above rocky cores. Their clouds shimmer with blues and greens. Their winds scream at supersonic speeds. They are cold on the surface, yet deep within, hidden warmth simmers, perhaps even oceans under exotic forms of ice. What makes them fascinating is how little we know. We've only visited Uranus and Neptune once, with Voyager 2 in the 1980s. Since then, they've been distant mysteries observed through telescopes, but never explored up close. Their tilted spins, faint ring systems, and stormy atmospheres remain puzzles waiting for future missions. They are like unread books on the shelf of the solar system. Neptune's great dark spot, a storm larger than Earth, once raged across its atmosphere, then vanished. Uranus rolls on its side, perhaps tipped by a massive collision in its past. These quirks remind us that even far-flung planets live dynamic lives shaped by accidents and forces long forgotten. Their secrets may include hidden layers of conductive water forming strange magnetic fields, or diamonds raining down through thick atmospheres. Exoplanet studies have revealed that ice giants are common elsewhere. Many stars host Neptune-sized worlds in close orbits, warmer and more active than ours. In studying them, we see reflections of our own distant giants. Each discovery reminds us that what seems rare nearby may be common across the galaxy. And as we consider giants, both fiery and icy, we should not forget the smaller companions, dwarfs that, though small, play vital roles in the architecture of systems. Dwarfs that count, the small but many. For a long time, we thought of planets as the main actors, but dwarfs, smaller bodies like Pluto, Eris and Ceres, remind us that size is not everything. These icy and rocky worlds may be small, but they are numerous. They inhabit belts, edges, and hidden corners, carrying stories of early formation. Each is a relic, a frozen chapter in the history of a solar system. Pluto, once called the 9th planet, was reclassified as a dwarf. Yet when New Horizons flew past in 2015, it revealed a world full of surprises, mountains of ice, plains of nitrogen, possible oceans beneath. Pluto may be small, but it is no less alive with mystery than any giant. The lesson is simple. Do not dismiss the small. They carry secrets the large cannot hold. Ceres in the asteroid belt also revealed hidden water and strange bright spots, salt deposits gleaming like eyes. Eris farther out may be even larger than Pluto. These dwarfs, scattered and quiet, are time capsules of the solar system's earliest days, less altered than bigger planets that underwent violent reshaping. They are like untouched ruins in an ancient city, whispering truths the monuments have lost. In other systems, dwarf planets may be equally important. They may carry water inward, they may act as reservoirs for organics, or they may remain as silent witnesses to planetary dramas. Their abundance reminds us that solar systems are not just about grandeur. They are also about persistence, about the small surviving in the shadow of the mighty. And sometimes, even the smallest of these worlds dress themselves in beauty, surrounding themselves with halos of ice and dust we call rings. Rings as planetary portraits. Few sights in the cosmos rival Saturn's rings. Delicate, shimmering, spanning hundreds of thousands of kilometers, yet only meters thick. They are made of ice, rock, and dust, fragments captured and shaped by gravity. Rings are not unique to Saturn. Jupiter, Uranus, and Neptune all have them, but Saturn's are the most majestic, a portrait of a planet dressed in light. Rings are dynamic, not static. Their particles collide, spread, and clump, forming patterns carved by the gravity of moons. Gaps like the Cassini division are sculpted by resonances, moons tugging on ring particles until voids emerge. The rings in this way are living systems of their own, shifting, reshaping, echoing the rhythms of their parent planet. What is astonishing is how temporary they may be. Saturn's rings are thought to be only a few 100 million years old, and they may vanish in another few 100 million. To witness them now is to live in a brief chapter of their existence. One day the planet may spin without its shimmering crown, the rings gone as quietly as they arrived. Rings tell us something about origins. They may form from shattered moons, from captured comets, or from leftover material never shaped into a moon. They are the jewelry of planets, but also their scars born from collisions and losses. Beauty and violence exist side by side, and out of destruction comes elegance. As you drift with the thought of rings circling in silence, the story pulls us toward their companions, the moons, each a world of its own, carrying dramas as rich as any planet. Moons. Second generations of wonder. If planets are the children of stars, then moons are the children of planets. They form in different ways, some from leftover disks around giants, some captured from wandering bodies, some born of colossal impacts. Each moon carries a history, and together they form a second layer of worlds within a system. Our own moon shapes Earth's tides, stabilizes our axis, and perhaps even made complex life possible. Imagine how many other moons, around other worlds, quietly influence their planets in ways just as profound. Jupiter alone hosts nearly 100 moons, from the volcanic Io to the icy Europa. Saturn, too, holds Titan, with rivers and lakes of methane under a thick orange sky. These moons remind us that habitability is not limited to planets. Some of the most promising places for life in our solar system lie not on worlds like Earth, but beneath the icy shells of moons orbiting giants. In their darkness, warmed by tidal forces, oceans may hide alien ecosystems waiting to be discovered. The diversity of moons is staggering. Some are potato-shaped rocks barely held together, others are larger than Mercury. Some orbit close in, locked in furious tides, while others wander far, tracing wide arcs around their hosts. The dance of moons adds complexity to planetary systems like smaller melodies woven into the main theme. Without them, the cosmic orchestra would sound incomplete. Moons also act as storytellers. Craters reveal ancient bombardments, smooth surfaces reveal internal activity, and hidden oceans reveal heat where none should exist. Studying them is like reading the footnotes of creation, small details that often carry the deepest meaning. They whisper truths about the planets they orbit, and about the forces shaping entire systems. And sometimes moons are not born with their planets at all. They are captured wanderers, drifting into a new family, adding surprises to the mix. Captured companions and family originals. Not every moon is native. Some are adopted. A captured moon begins as a passing asteroid or dwarf planet caught by a giant planet's gravity. Once trapped, it becomes part of the system, circling its new parent like a guest that never leaves. Our own moon is not captured. It likely formed from an impact, but many small moons of Jupiter and Saturn are captives, drawn in from the solar system's outskirts. Captured moons are often irregular, with tilted orbits, strange shapes and unpredictable paths. They reveal the restless history of planetary systems where migration, collisions, and chance encounters shape outcomes. Each captured companion tells us that solar systems are not closed loops. They exchange pieces with one another, scattering and gathering across space like traders on cosmic roads. These adoptions also hint at how water and organics may have been delivered inward. A captured icy body can bring reservoirs of frozen material to a system, seeding it with the ingredients for oceans, atmospheres, or even life. Captures are accidents, but their consequences can be profound, rewriting the destiny of entire planets. What seems like chaos is often the source of hidden order. Some moons are hybrids of sorts, born from the original disk but reshaped or disturbed by captures. Systems become mosaics, half native, half adopted, each piece adding texture to the whole. And when tides come into play, the relationships deepen, turning gravitational pulls into heat, reshaping worlds from within. Which brings us to one of the most extraordinary truths of moons. Their tides do not just move oceans, they create warmth, carving landscapes, and even keeping hidden seas liquid beneath frozen shells. Tides that warm, tides that shape. On Earth, tides rise and fall with the moon's pull, shifting waters gently along coasts, but in other places tides are far stronger, powerful enough to heat worlds from the inside. Jupiter's moon, Io, is the most volcanic body in the solar system, not because of sunlight, but because of tides. Jupiter's gravity pulls at Io relentlessly, flexing its crust, generating heat that fuels endless eruptions. Here, tides are not just gentle rhythms, they are furnaces of creation. Europa, another moon of Jupiter, experiences similar tidal flexing, but with different results. Instead of fire, Europa's tides keep an ocean beneath its icy surface liquid. This ocean may be twice the volume of all Earth's oceans combined. It exists in complete darkness, warmed not by the sun but by gravity's pull. If life exists elsewhere nearby, Europa is one of the likeliest places. Tides turn an icy shell into a cradle of possibility. Saturn's moon, Enceladus, offers a similar story. Its south pole vents plumes of water into space, evidence of an underground ocean kept warm by tides. These geysers contain salts, organics, and energy, three of the key ingredients for life. It is as if Enceladus is whispering to us, spraying clues into space for us to find. Without tides, it would be a frozen rock. With tides, it is alive with mystery. Tides remind us that energy in the universe is not only about distance from stars. Gravity itself can create heat, stir oceans, and keep worlds dynamic. In this way, moons extend the range of habitability far beyond where sunlight alone could reach. Planets may not need to be in the habitable zone if their moons are warmed from within. And once tides set the stage for warmth and possibility, another element becomes essential: the thin, fragile veils that worlds wear, atmospheres. Atmospheres, thin veils, thick oceans of air. An atmosphere is more than air. It is a shield, a climate regulator, and often a sculptor of landscapes. Some planets have atmospheres so thin they can barely hold heat. Others have layers thicker than oceans, pressing down with immense weight. On Earth, our atmosphere is a miracle of balance, enough to protect, enough to breathe, not enough to crush. It makes life possible, and it colors every sunrise and sunset we see. Mars, with its thin atmosphere, reveals the consequences of loss. Once, it may have had rivers and lakes. Today, it is cold and dry, unable to hold warmth. Venus, in contrast, shows the danger of excess. Its dense atmosphere traps heat in a runaway greenhouse, baking the planet hotter than Mercury, despite being farther from the Sun. The contrast between Mars and Venus shows how fragile this balance is and how a slight shift can transform a planet's fate. Atmospheres also reveal character through chemistry. The blue of Neptune, the orange haze of Titan, the pale glow of Earth, all are products of what lingers in their skies. By studying atmospheres, astronomers can read a planet's story, what it is made of, what processes shape it, and even whether life might be altering it. A thin veil carries profound truths. Exoplanet atmospheres, though faint, can sometimes be detected as starlight filters through them. Signatures of water vapor, methane, or carbon dioxide whisper of conditions far away. The hope is that one day we may read in these signals not only chemistry, but biology, a fingerprint of life hidden in a distant sky. The atmosphere is a window both out to space and inward to possibility. And when we look closer, atmospheres are not just gas. They are shaped by what floats within, clouds, hazes, and colors painting worlds in endless variety. Clouds, hazes, and the colors of distant skies. Clouds are storytellers of atmospheres. On Earth, they bring rain, shade, and beauty. On Jupiter, they form stripes of ammonia and hydrogen swirling endlessly in storms larger than our planet. On Titan, clouds of methane drift across orange skies, raining hydrocarbons onto alien lakes. Each world wears its sky differently, its clouds painting portraits of chemistry and climate. Looking at them is like looking at moods written across the heavens. Hazes, too, play their part. Titan's thick haze blocks sunlight, giving it a permanent twilight. Venus glows yellow-white under sulfuric clouds forever shrouded. Neptune's haze deepens its blue, making it shimmer in a way that feels almost unreal. These hazes scatter light, giving each planet a distinct appearance. The colors of skies are not only beauty, they are physics, scattering molecules dancing with starlight. In distant exoplanets, astronomers detect hazes that obscure everything below. Some worlds are wrapped in cloudy veils so thick that no surface can be seen, yet even these hazes tell stories. What chemicals are present, what temperatures dominate, what processes churn within. A cloudy sky is never empty. It is always a clue, a layer of meaning waiting to be read. The beauty of clouds is also their impermanence. They shift, form, and vanish, reminding us that skies are alive. Saturn's great white spot erupts every few decades, a storm so vast it wraps the entire planet. On Earth, too, we find patterns repeating but never identical, a dynamic balance of water and air. The same principle plays out on planets light years away, in storms we can only imagine. And behind these veils the story grows deeper, where balance of heat and gas becomes unstable and worlds tip into climates that spiral toward extremes. Greenhouse balances and runaway edges. An atmosphere is more than just a layer of gas. It is a thermostat. Some planets get this balance right, trapping enough heat to keep oceans liquid and climates steady. Others tip too far. Venus shows us what happens when greenhouse gases run wild. Carbon dioxide there creates a furnace, pushing surface temperatures high enough to melt lead. Mars, on the other hand, lost too much atmosphere, leaving it cold and dry. Earth balances between these edges, fragile, yet stable enough for life to flourish. The greenhouse effect itself is not bad. It is life's ally. Without it, Earth would be a frozen desert. The danger comes when it spirals out of control, trapping more heat than the planet can release. On Venus, sunlight warms the surface, the heat gets trapped, and the cycle compounds endlessly. It is a reminder of how thin the line between paradise and wasteland truly is. On distant exoplanets, astronomers suspect similar stories unfold. Some worlds may be Venus-like, cloaked in suffocating skies. Others may balance closer to Earth, holding oceans under protective blankets. The greenhouse effect is universal, a law of physics that shapes climates across the galaxy. By studying it, we learn not just about other planets, but about our own delicate future. This balance also shifts with time. A young star grows brighter, slowly moving the habitable zone outward. Planets once perfect for life may overheat, while frozen ones thaw. Greenhouse balances are not permanent, they are chapters, each lasting millions or billions of years. Life, if it arises, must adapt or perish with the changing climate of its world. And while atmospheres protect, they are also vulnerable. Without another layer of defense, something stronger than air, planets risk losing their precious balance to space itself. That's where magnetic shields step in. Magnetic shields and silent storms. Beneath Earth's surface, molten iron moves like a slow river, generating a magnetic field. This invisible shield extends far into space, deflecting solar wind and protecting our atmosphere. Without it, our air and water might have been stripped away long ago, as happened on Mars. A magnetic field is like an unseen guardian, standing against storms from the star, keeping the conditions for life safe below. We see its work in auroras. When charged particles slip past the shield, they spiral into the poles, colliding with air molecules and painting the sky with shimmering lights. The northern and southern lights are beautiful reminders of the invisible battles always being fought above us. Behind their beauty lies a serious truth. Without this shield, those storms would erode the very air we breathe. Other planets reveal variations. Jupiter's magnetic field is immense, so large it would cover much of the night sky if visible from Earth. Its power traps radiation around the planet, creating harsh zones for spacecraft and moons. Mercury, tiny as it is, somehow maintains a weak magnetic field, puzzling scientists about how such a small world sustains it. Mars, lacking one, sits vulnerable, a world stripped and scarred. Exoplanet research now looks for magnetic shields too. A planet may orbit in the habitable zone, may have water, may even have an atmosphere, but without protection from stellar winds, it may not hold them for long. The shield is as important as the air itself, silent yet decisive. Life's chances depend on it, though it cannot be seen with the eye. And beyond shields and storms, space itself has a weather system, a flow of energy from stars that stretches across worlds, shaping their skies in ways both violent and beautiful. Space weather, from flares to auroras. The sun is not calm. It pulses, flares, and hurls streams of charged particles across the solar system. These solar winds and eruptions create what we call space weather. On Earth, space weather can disrupt satellites, power grids, and radio signals, but it also paints auroras, the shimmering curtains of green, red, and violet light that dance near the poles. Space weather is both danger and beauty, always present, always shaping. Solar flares release bursts of X-rays and radiation in minutes. Coronal mass ejections follow, sending billion-ton clouds of plasma racing toward planets. When they strike Earth, our magnetic field shields us, but technology feels the impact. In ancient times, such storms only created auroras. Today, they can affect entire civilizations. We are more vulnerable than we realize, tethered to a star that breathes fire. Other planets feel it differently. Mars, with little shielding, is blasted directly, its atmosphere slowly eroded away. Jupiter's moons, locked in its immense magnetic field, experience radiation storms thousands of times stronger than Earth's. Even icy worlds at the edge feel the ripple of the sun's moods. Space weather is not confined to near space. It is a system-wide phenomenon, an invisible heartbeat of the star. Exoplanets orbiting active stars may endure far harsher space weather. Red dwarfs, common in the galaxy, flare often and violently. Planets close to them may be sterilized again and again, stripped bare of atmospheres. Yet some may endure, protected by thick blankets of gas or powerful magnetic fields. The balance is delicate, but where it holds, life may still take root despite storms. And when space weather interacts with surfaces, it leaves marks, craters, scars, and landscapes shaped by collisions that began as cosmic bullets racing through space. Impacts, sculptors of crusts and histories. Every world wears scars, craters on the Moon, plains on Mars, even Earth's hidden basins, all tell the story of impacts. In the early days, collisions were constant. Planetesimals crashed together, shaping planets through violence. Some impacts destroyed, others created. Our Moon itself may have been born from a collision with a Mars-sized body. Impacts are not only endings, they are beginnings too. Look at Mercury, its surface pocked with countless craters. Or at Mars, with basins so vast they reshaped the planet's history. Even Earth, with its oceans and weather, hides scars under erosion, yet the record remains. The Chicxulub impact 66 million years ago changed the course of life, ending the reign of dinosaurs and clearing the way for mammals. A single collision shifted the story of an entire planet. Impacts also deliver. Comets and asteroids carry water and organics, striking young worlds and seeding them with the ingredients of life. Earth's oceans may owe their existence to countless such deliveries. Destruction and creation walk hand in hand, reminding us that chaos and beauty are woven together in the universe's design. Elsewhere, impacts continue. Saturn's moons show fresh scars, evidence of recent strikes. Even distant Pluto carries a landscape reshaped by collisions. Exoplanets too may bear similar histories, their surfaces scarred in ways we cannot yet see. Wherever matter collides, it leaves testimony written in stone. But planets are not only sculpted by falling rocks. From within, they change themselves through fire, eruptions, and the slow recycling of their crusts. Volcanism and the recycling of worlds. Volcanoes are the voice of planets, speaking from their depths. On Earth, volcanism builds mountains, creates islands, and recycles carbon into the sky. It is a process of renewal, connecting the inside of a planet to its surface. Without it, Earth's climate might not have stayed balanced, and life might not have found the stability it needed. Volcanoes are destructive in the moment, but vital across time. Io, Jupiter's moon, erupts constantly, its surface remade again and again by volcanic fire. Enceladus, though tiny, shoots geysers into space, its plumes carrying water, salts, and organics. Venus, shrouded in clouds, may still hide active volcanoes beneath its glowing skies. Wherever we look, volcanism appears, reshaping, recycling, reminding us that worlds are never truly still. Volcanism also creates diversity. Rocky planets with active interiors are more likely to host dynamic climates. They release gases, build land, and sustain magnetic fields. Dead worlds with cooled interiors grow silent and barren. Mars, with its towering Olympus Mons, once erupted fiercely but now sleeps, its energy gone. Earth, still alive inside, continues its cycle, reminding us that activity below sustains life above. Exoplanets too may experience volcanism on scales we can scarcely imagine. Super-Earths with greater gravity may host eruptions larger than anything on Earth. Some lava planets may have entire surfaces reshaped daily. Volcanism is not just spectacle, it is survival. It is how planets breathe, how they exchange materials between inside and out. And sometimes volcanism hides oceans beneath ice, stirring warmth in unexpected places, creating secret habitats where life may bloom far from the light of any star.